Hello, this is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. In this lecture, we're going to talk about Learning Objective 1.1, Rectilinear Kinematics. Just as a reminder, this is Chapter 11 of our Beer and Johnson textbook, focusing on particle kinematics. And when we talk about particle kinematics, it's really broken into two subcategories. That would be rectilinear motion versus curvilinear motion. On the right, you see an example of curvilinear motion, but on the left, we have an example of rectilinear motion. Rectilinear motion is typically thought of as 1D motion, i.e. movement along a line. That's why I got a picture of a drag race. They're just going straight ahead. They don't need to turn or anything. So we got 1D there, as opposed to curvilinear motion, looks at some curving, hence the sprint racing on the other side. We could talk about this in 2D or in 3D, though in this class we'll limit our study to 2D curvilinear motion. Makes life a little bit easier for us. Additionally, when we think about this motion, like we said, this is going to be in a straight line. And though motion is always a vector, it's going to have both magnitude and direction. If we're thinking about it in rectilinear terms, that vector can be kind of modeled as a scalar. So the idea is that as you move along that line, you're going to have positive and negative values, and that gives you all the direction information you need. However, in curvilinear motion, we can have curved lines, curved path, which means we always have to use vector notation of some sort, like we mastered in statics in Calculus 3. Although we can think of things as having scalar motion along the path. So scalar motion along the path. So that seems pretty clear, I think. So 2D, 1D. We're going to start off talking about one-dimensional motion. And so specifically, we want to talk about those rectilinear kinematic properties. If you're following along in your FE reference handbook, this is on page 77. Remember, you can take notes in your FE reference handbook to use during your exam, although I do ask you not to use example problems in your FE reference notes. Typically, that creates problems anyways on the exam. And so when we talk about this, we're going to have a couple of different categories. We're going to have position, velocity, and acceleration. Velocity, and now I need a little bit more space, so I'm going to take this away. Remember, right now we're just focusing on our rectilinear one-dimensional motion. Velocity and acceleration. Okay, so that's what we've got going on here. Now, the notation that we're going to use for these things, position is going to be, in your book, chapter 11, it uses the symbol X. The FE reference handbook, and later in your book, we use the symbol S for scalar position. When we think about position vectors as a whole, we're going to use the symbol R. This is the same as what we did in statics. And it's important to recognize that this is typically thought of as a function of time. And so if we were to plot our position, our x-axis would be the time, and then our position would be plotted on the y-axis of our curve. And I'll show you that in just a second. This will be signed, meaning that it can be positive or negative relative to some origin. Its magnitude for position is just distance, which is going to use units of either feet for US customary or meters for SI units. And so again, position S or R. Now velocity, we're going to use the symbol V, and that's how I draw my V's. I'll increase this a little bit because I don't think we need the screen all that much for the moment. So you can see we got position, X, S, and R. and then velocity v going on there. Now, the velocity is also, in rectilinear motion, we can think of it as a scalar. Sorry, yeah, we can think of it as a scalar, but really it is a vector, And this is going to have a sign as well. I'm going to leave some space here to fill this in as we think this through. It can also be plus or minus, and it doesn't need to be the same or different from the position. So there's a relationship between these two, but it's not a one-to-one relationship. Just because my position is positive, my velocity can be positive or negative. The magnitude, we have a special name for the magnitude, and that's speed. And so typically we'll just indicate that without the hat. So strictly speaking, we have velocity and our speed and velocity. And this is where I would say we're familiar with the idea of using rectilinear properties when thinking about our velocity, because you're used to looking at a speedometer that only tells you the magnitude of your velocity. It doesn't tell you your direction. So we can have that going on there. And then our units will be length over time. So maybe you're familiar with miles per hour or feet per second or meters per second. And so that should start to give you a little indication of what's happening here with the relationship between position and velocity. Now, acceleration, same thing. Rectilinear, we can think of it as scalar, but really it's going to have a vector hat like there. The sign, it can be positive or negative. Doesn't depend on, well, I mean, there's a relationship, but it doesn't have to be the same or different from the others. Magnitude is just going to be acceleration without the hat. Yep, acceleration all by itself. We don't have a different word for that. And its units will be in length per time squared. So meters, let's see which direction we're, feet per second squared, or meters per second squared. And I hope acceleration brings to mind the acceleration constants due to gravity that would tell us that our acceleration is going to be 9.81 meters per second squared or 32.2 feet per second squared for an object falling on Earth. So that's a thing. Now, we got to think through the relationship between these. So I've given myself some space on the board. I hope you have in your notes as well. And what I'm going to do is I'm going to switch over to look at an experiment we're going to run real quick. On the left, you can see a Pocket Lab I have set up in the room, and this is going to be interacting with, I apologize for the screen glitching out like that. This will be interacting with the this cart here. So what I'm going to do is, if you'll notice on the top, it has position, and then it has velocity, and then it has acceleration. So I'm going to start my recording. We notice that the position starts out negative. That's fine. We're not too worried about that. But if I now move my cart back and forward, oh, he fell off, and bring him to a stop. I've got some data there for us to work with. I can press stop. Okay. And now we can play with this in relation to what's happening there. So you can see where my position started off. It looks like I have a little bit of a zeroing problem, but hopefully that won't create too much of an issue for us. Okay, so we got our zero values right through here. And then we saw where the motion went negative. So that was, here we can play the video again just to see which direction was negative. Okay, so down low was negative, and then it went positive, and then back to negative, and I had to kind of stop, and then we moved it back to zero. So that's our position, or back to the middle, I should say. It's not really zero. So that's our position information. That's pretty cool. So we can zoom in on that area of interest there. So that looks pretty good. Hopefully that makes sense. Now, when we look at velocity, I want us to notice some things. Okay. First thing that we want to notice is that when position was at its peak and then it started to turn back around, at the same time, the velocity was just about zero. Do y'all notice that? And if we look at the slope, so the change in position through here, it's a negative slope, and we see negative velocity, right? Yeah, slope of position, negative velocity. When the slope changes, I now have positive velocity. Again, if I go to my next peak, right here, I can actually get it to hit. We'll notice that at that peak, the position is basically back to zero, or the velocity is back to zero. So my hope is that as we talk about that, there's a light bulb going off in your brain about math and calculus and how those things might relate. Well, it turns out that velocity can be thought of this way. We're going to have the change in position divided by the change in time. So this would be our average velocity. So if we think about it in the Charleston area, if we were to drive to Columbia, we might say that takes us 2 hours. And it's about 100 miles. So if we look at our change in position, about 100 miles, and we divide it by our time, about 2 hours, we're doing about 50 miles per hour. And that's all fine, average velocity. But what happens is if we apply a limit where delta t goes to 0, we start to get an instantaneous velocity. And we would indicate that with a ds dt, or if we're doing it in vector form, a dr dt. So we're going to take the derivative of position with respect to time, and that's going to be our velocity. So velocity is the change in position with respect to time, or we can think of it this way, the slope of our position as a function of time. Okay? Change in position with respect to time, or the slope of our position with the function of time. Or we can even think of it as the rate of change. So if we had our average velocity as what we were doing to Columbia, the instantaneous velocity, that's what the police officer gets with his radar gun. Right? So that's what he's going to measure, is how fast you were going at that moment. And so if we look at our chart here, we can see where that relationship falls together. So we have a peak. Sorry, I got to touch it here. We see that relationship. Where there's peaks, we get zeros because the slope goes to 0. And when the slope is positive, we have positive velocity through that region. Right? Now the next step that we go to is to acceleration. And so acceleration, if we notice that, if we go to the peak in our velocities, which is now an inflection point on our position, right, that we can see a roughly 0 value in our acceleration. And that's because we're doing this derivative again. So again, if we go here to a peak, and let's look at this peak. Let's look at this peak in the velocity. We see that our acceleration is at an inflection point, roughly, and our position's an inflection point, and our acceleration's roughly at 0. So hopefully that gives you a good sense for that relationship. And so what we see is that acceleration is the rate of change for velocity. So again, we can think about the average, dv dt, right? The average change in acceleration. But if we do that limit as delta t goes to 0, we're going to have dv dt, like so. And we can put our little vector hat on there. And so this is going to be the rate of change in velocity. Or we can think of it as the slope of the velocity with respect to time. Okay, it's pretty cool. Now there's one more relationship that we might want to add to our FE reference handbook. It tells us that not only is acceleration equal to dv dt, we could substitute this in and we would find that it's going to be equal to dr dt squared, so the derivative twice of the position. And then there's another relationship that your textbook proves that we can also write acceleration this way. Or we can talk about it in scalar terms. Right, so this is how your textbook actually talks about it. Something like this, where we have the velocity times the change of velocity with respect to position. And so we'd want to take advantage of that in some of our work. All right, so I hope our little demo there helped you see that. Now I'm going to close this out in the hopes that the camera will stop glitching and smooth out a little bit. Okay, so here's all of our information. We got position, we got velocity, we got acceleration. To move from position to velocity, we're going to take the derivative with respect to time. And to move from velocity to acceleration, we're going to take the derivative of the velocity with respect to time. If we think about that in terms of position, we can do it twice. Sorry, left off a notation thing. Or we can think of it as the velocity times the derivative of the velocity with respect to position. So all sorts of good math going on here. Remember, as an engineer, math is a tool. Now, what this brings us to is the great circle of kinematic properties. So I buy myself some space, because what we're going to want to be able to do is move between velocity and acceleration. So when we think about this, we might start with position as a function of time. Position as a function of time. And if I wanted to move up to velocity as a function of time, I would simply have to take the derivative of position with respect to time. Okay, that's the relationship we just stated. And if I wanted to go and calculate the acceleration, I would take the derivative of the velocity with respect to time, which is the same as the second derivative of position with respect to time, which is the same as velocity times the change of velocity with respect to position. So we've kind of got this path sorted out. So if we enter the circle, we're given velocity, we can work our way over to acceleration. Now, if we're given acceleration, let's say we wanted to work our way over to velocity. Well, how would we do that? We would do that by integrating. So our velocity with respect to time is also, not only is it equal to the position, the derivative of the position with respect to time, it's equal to the integration of acceleration with respect to time, like so. Now the trick to doing this is that we have to keep track of what our constant is going to be based on whatever initial conditions we have. So we are going to have an integration constant. And then finally, if we were given velocity and asked for position, we might work our way back up to here by integrating velocity with respect to time. And so with our great kinematic wheel, we can work our way around depending on where we are given data and where we start. And so with that, we are really set in many ways to try and tackle a problem. And so if we look at this problem, we're given position as a function of time. And how do we want to move from position as a function of time to velocity? Well, we take the derivative, right? And so when we take that derivative, we see this relationship. Now it's important for us to recognize, and this chart makes it just a tiny bit easier, to note that when we have the peak, we see an inflection point. When it goes to 0, it's at the peak. So we see those mathematical relationships. And we can also see where in this case, all of our position data is positive up till 6 seconds in, but our velocity goes from positive to negative. And so if we think of what the particle is doing here, it's actually, see, the velocity is increasing, and then it starts to slow down, but it's still moving in the positive direction. And then when it hits the max, it starts to head back, and so our velocity goes negative. So that's how we go there. Now, and we can see those mathematical relationships. Again, if you notice, I've included in my math these units. Now, your textbook doesn't always do this, nor do many people in general, but I find it very helpful because when I plug in my units, my numbers, I'm always going to include units. And we'll notice here that if I put in time, the seconds will cancel and the seconds will cancel. I'll be left with meters, which is the appropriate unit for position. Likewise here, when I change this, I'll be left with meters per second. Now, if I want to go from velocity to acceleration, I can do that by taking the derivative again, right? Velocity to acceleration. And we'll notice that our acceleration starts positive. It goes to 0 when the velocity maxes out. The acceleration is actually acting in the negative direction. This is like pressing the brake pedal, right? Slowing down. And then eventually it drops into reverse. And so now we're accelerating in the other direction. And my units again work out. I have meters per second squared. That's my initial condition. And then once I multiply by time, those will cancel out again. So hopefully that's clear to you. I know this has been a long video, but this is rectilinear kinematic properties. We'll work a problem together in class after the next video. Thank you.